Hi guys, in this video we are going to continue our discussion of valence bond theory, which provides this quantum mechanical description of bonding in atoms, between atoms and forming molecules. Okay, and specifically, we're going to be focusing in on a very important concept, this concept of hybrid orbitals. And what we're going to see is that through the formation of these hybrid orbitals, we're able to mix together atomic orbitals, the orbitals that we learned about when we were studying quantum mechanical properties of atoms. We're going to be able to mix these orbitals together to get new mixtures of orbitals with some very interesting and unique properties that are going to allow us to understand and describe and ultimately predict the bonding interactions in arbitrarily complex molecules. Okay, so to frame this discussion, let's recap real quick here the core assumptions going into the valence bond model. Right? First and foremost, what we're doing here is taking into account quantum mechanics. In other words, we are keeping this fact that electrons reside in orbitals front and center in our minds. And we're going to recall that there are a whole bunch of orbitals that we learned about in that quantum model of the atom discussion from previous lecture that are going to be really serve as our building blocks for building up these more complex bonding models. So our S, our P, our D, and our F, and so on and so forth, all of these orbitals are going to be coming into play. And remember, within the valence bond model theory, we are describing covalent bonds as the overlap between these atomic orbitals. So if you have two half-filled atomic orbitals with only one electron in them, those two orbitals can come together. They will then form one longer orbital here, right? This overlap between them, you can represent it like this, right? And that larger orbital will then describe the bonding arrangement for those electrons that are essentially gluing together these two nuclei. Okay, so that's our covalent bond, right? Electron pairs occupying this new orbital that's formed through the overlap of these isolated atomic orbitals. And we saw previously that this simple bonding model right off the bat has a number of successes. One of the successes is, for example, predicting the bonding arrangement geometry in H2S. Right, so H2S, obviously, we've got two hydrogens and one sulfur atom, and that sulfur atom has two vacant p orbitals, half-filled, half-filled p orbitals, two half-filled p orbitals and two half-filled 1s orbitals, one from each of the two hydrogen atoms. Those orbitals can come together and form sigma bonds, right? So two sigma bonds. So we have one sigma bond here and another sigma bond here. Okay, and we find out that this bonding arrangement that we would predict by this simple model involving these atomic orbitals, p orbitals and s orbitals, right, actually provides a geometry that's in very close agreement with experiment. So the p orbitals, as they stand, as they come out in terms of our discussion from the quantum mechanical structure of atoms, we've got these three different sets of these three different p orbitals that are all 90 degrees to one another. Okay, and the experimental geometry is for this SH bond angle, the angle between these two sigma bonds here, is in fact 92 degrees. So we do a pretty darn good job. However, the general problem of being able to describe arbitrary geometries, we're not able to do it if we're relying solely on these individual atomic orbitals. So the example we saw last time was an attempt to describe the bonding interaction in the simplest hydrocarbon we could imagine, a single carbon atom and hydrogens added to that single carbon atom. We see that if we rely on atomic orbitals, we are left with only two bonding possibilities. There's only two half-filled p orbitals that will then overlap with the two half-filled 1s orbitals from each of two different hydrogen atoms, and you will predict a structure that looks very similar to the H2S. But right off the bat, we know that this structure is incorrect. We know from even a simple Lewis structure analysis, this structure is incorrect. We know the correct structure has 4 hydrogens attached, and that those 4 hydrogens are at 109.5 degrees apart from one another, right? The bond angle here is not just simply 90 that would be predicted based on the structure of isolated p orbitals on individual atoms. Right, so we've got a couple problems here. So what we're going to need to do is expand valence bond theory in order to be able to describe situations such as this methane molecule right down here at the bottom. All right, so this is where the concept of hybrid atomic orbitals comes in, right? So we're making this distinction. If we say atomic orbital, and I'll oftentimes abbreviate that AO, these are the results of quantum mechanical calculations performed on individual atoms. There are no other atoms present. We're not talking about molecules. We're doing quantum mechanics on individual atoms. And these are all those standard orbital shapes that you've come to know and love. Now, hybrid orbitals, on the other hand, these are mixtures of atomic orbitals. So they're mixtures of atomic orbitals, and we're going to mix atomic orbitals together in a certain way that will allow us to very accurately approximate the results of quantum mechanical calculations on molecules. All right. Now, I'll come back to this again in the next unit when we talk about molecular orbital theory, but I want to remind you that quantum mechanics, it's very hard to solve quantum mechanics problems. There are a number of algorithms out there that we can, approximate Schrodinger's equation, do a pretty darn good job, but actually coming up and predicting the orbitals on molecules is quite a challenge. And in fact, it's something that we can't even do, exactly, for all but, trivially simple molecules. So what we're doing here is we're approximating quantum mechanical results. These are not quantum mechanical results in and of themselves. We're using quantum mechanical results on atoms to approximate the results on molecules. Okay, that's what a hybrid orbital is. So for example here, I could take the s orbital and a p orbital and I could mix them together. And if you add them together, subtract them together, take into account phases, blah, blah, blah. All right, we're not going to go into all the mathematical details here. You can construct a new set of orbitals that have distinct orientations and distinct shapes, like I've got illustrated here. Okay, and so what we're basically going to do in this lecture is work through a handful of hybrid orbital schemes, right? Mixtures, certain combinations of atomic orbitals that are useful for describing molecular geometry in general. Okay, so to kind of lead into this concept of hybrid orbitals, it's important, I think, to perhaps consider an example, right? Where in this example we're asked to use valence bond theory to try and describe beryllium chloride bonding. Okay. Now, hopefully at this point you can all draw out that beryllium chloride Lewis dot structure. So number one here, our first step in trying to predict this bonding arrangement and what orbitals are involved are to actually go back and rely on what we already know. Look at those valence electrons, figure out where they are, build that Lewis dot structure, and then go on from there. Okay. So we've got our Lewis dot structure with that single beryllium atom with 2 bonds to chlorines on either side. Now, if we are going to try and construct a bonding model for beryllium chloride, well, what we're dealing with here, we're looking at a second row element. So the valence orbitals involved in this second, or associated with this second row element, are of course the 2s and the 2p orbitals. In the case of beryllium, what we're going to see is actually 2 electrons in an s orbital and 0 electrons in a p orbital. Now you can see right off the bat, this just gives us a whole slew of different problems. First of all, there isn't a half-filled orbital. So you're left with all these different options. Well, okay, if I want to try and, make an overlap between half-filled orbitals, do I use p orbitals? Well, if you use p orbitals, you'd be getting this bent geometry. You wouldn't be getting a linear geometry. If you used 1s and 1p, right, you could get the linear geometry, right, because you could imagine a situation where remember the s orbital is right on top here. You can get this s orbital overlapping with one chlorine, this guy overlapping with another chlorine, right? And then, yeah, okay, you've got a linear geometry, but now those bonds aren't the same length, right? So really, no matter what you do with that ground state electron configuration with the orbitals, atomic orbitals, as they're populated in the solution for Schrodinger's equation for that isolated atom, you simply can't account for the bonding, right? We're dead in the water. Okay, so what we need to do is, of course, mix together these s and p orbitals in some sort of way so that we can construct differently shaped orbitals such that their shape, orientation, and energy, all right, can adequately account for this linear geometry that we know to be true. Okay, and this brings us to the example of hybridization that simply involves mixing together an s and a p orbital. So if you mix together an s and p orbital, what you end up getting at the end of the day is two different orbitals that have the same kind of structure as this dumbbell, right? But the dumbbell is now lopsided, right? If I have an s and a p coming in, you're going to get two different sp orbitals, as we're going to call them, coming out, right? But now the dumbbell is lopsided. You're either going to have extra electron density on the left-hand side, like we have for the first one here, or extra electron density on the right-hand side, okay? But by doing this, by forming these two hybrid orbitals that are identical orbitals just rotated in space, right, we will end up with a bonding, of the possibility for bonding that can actually account for this linear geometry. So to see this, notice that if I superimpose both these sp orbitals, here's the first one, here's the second one, on beryllium, well, we're now directly set up for overlap with a lobe of the chlorine. And of course, the chlorine, we'd be looking at p orbitals on the chlorine atoms. We've got a chlorine here, right? We can get that overlap. And because we've formed two equivalent sp orbitals, the only difference is their orientation in space, they are going to have the same energy, right? Which means if I have two electrons and I've now formed two different orbitals at the same energy level, we are going to use Hund's rule and predict that each one of these sp orbitals will actually only have a single electron in it, which is another win for us because now we effectively have two half-filled two half-filled orbitals that are now ready to engage in that bonding. So to see a little bit more complete picture of this, we can consider the orbitals in our example of beryllium chloride here that are actually involved in the hybrid orbital bonding picture using these sp hybrid orbitals. The chlorine atom will obviously have a bunch of lone pair electrons, 3 sets of lone pair electrons that will be on different orbitals, but the chlorine atoms will have half-fill set, right? That 7th electron, that 7th valence electron associated with chlorine, right, will be sitting in a half-filled orbital, right? We can draw it something like this. And the beryllium, right, the beryllium atom will have these two half-filled sp orbitals, right? So we can get this orbital overlap to form bonds, right? And there'll be two of these bonds, and these two bonds then are going to be exactly equivalent because the two sp orbitals are exactly equivalent in terms of energy and actually shape. So the bond lengths will be the same. All these desired properties essentially fall out. So we're able to describe bonding, this linear bonding arrangement with beryllium chloride and the formation of two equivalent sigma bonds, right, using this hybrid orbital sp orbital that's built by mixing together s and p orbitals. Okay. And so I want you guys to remember that this process of orbital mixing is a mathematically defined process. Each one of these orbitals represent mathematical solutions to the Schrodinger's equation or approximations to solutions of the Schrodinger equation, right? And so what we're doing here when we're mixing together these different mathematical functions is building up new mathematical functions that have different energies, shapes, and orientations, okay? So there is a mathematical footing for all of this, right? But we're not going to go into any of the mathematical detail. I want you guys to just remember the results, okay? And so I've illustrated both of these core results for SP hybridization on this summary slide here. So if you are carrying out an SP hybridization, you're mixing together one p orbital, one s orbital, putting them together to get two equivalent sp hybrid orbitals. And so as a result, we haven't touched these other two p orbitals. Those remain unhybridized, right? And so from an energy standpoint, we now have two orbitals, sp orbitals, that have an energy that's somewhere in between the original s and p. So remember, we're taking on characteristics of both the s and p, including their energy. We're looking at a sort of averaging sort of effect, okay? So those energies are somewhere in between. So we're looking at our energy axis here, somewhere in between. And they're going so as a result, right, this affects the electron distribution, and of course I was going to really pave the way for building up these covalent bonds according to the valence bond model, okay? And then the second thing I want you to remember is the geometric consequences of this sp hybridization. By mixing together one s and one p orbital, you're mixing together two orbitals, you're going to get two orbitals out on the other end, and these orbitals look like these asymmetric dumbbells. So p orbitals that one side got really fat, okay? And those, the blue dot here that I'm now covering up, right, that is the nucleus. And so if we superimpose both of these sp orbitals on top of one another, we end up with two orbitals that are equivalent, that are all aligned right along this line here, right? And so that's why these sp hybridization is so effective at describing linear geometries, right? Mathematically, we come up with two sets of orbitals that lie directly on the same line. Okay, so as soon as we do this, we can already start to solve some rather intricate problems here. So I want to go ahead and jump into one of those examples. Specifically, I want to look at acetylene, right? Compound where, again, the Lewis structure is fairly straightforward. C2H2, you've got a triple bond between the two carbons, right? But what we want to do is use that hybridization concept, this sp hybridization concept, to really understand what kind of orbitals are overlapping in this bonding picture. So the first thing we're going to do, right, we know this geometry is linear. So as soon as we know that the geometry is linear, we know to start looking at this sp hybridization. And so the purple orbitals here are sp orbitals localized on that carbon atom. Right? And so both of the carbon atoms in acetylene undergo this sp hybridization, then you are going to get two, right, equivalent sp orbitals, right? One going to the right on a given carbon, the other going to the left. The ones pointing towards each other, the two sp orbitals pointing towards each other between the two carbons, are going to overlap to form a carbon-carbon sigma bond. Right? And so we'd oftentimes denote these bonds by saying, okay, where is that electron density? Is it on the axis, off the axis? Right? This one's on the axis. It's a sigma bond. We say what elements are involved in the bonds. We label the chemical symbol of those elements, carbon in both of these cases, and then the type of orbital that is overlapping in the formation of that bond. So sp and sp in the case of this purple bond right here in the middle. Okay, and then of course on the ends, the other carbon sp orbital overlaps with the hydrogen 1s orbital, and we get our bonds to each one of the hydrogen atoms. And now what's left over on each one of those carbon atoms are two more p orbitals, each one with a single electron. And remember, those p orbitals are located, right, perpendicular to the plane or the line in which these sp orbitals lie. and the two different p orbitals are mutually perpendicular to each other. And so that's what this diagram is illustrating here with these orbitals in red. We've got a p orbital with a single electron up top here, another p orbital with a single electron kind of coming out of the screen at you, and the same sort of picture over here on the other carbon. And so you have side-by-side overlap between these two sets of p orbitals, and that results in the formation of not one, but actually two pi bonds. And so that first bond in acetylene, we can think of it as like our sigma bond here, but then there's an additional 1, 2 bonds that are formed through this side-by-side overlap, and which are we know are of course pi bonds, and so those are labeled here, right? Again, pi bonds, and those are formed between carbon p and carbon p orbital overlap. Okay, so now you can kind of see in action, something that I mentioned earlier in a previous video, where that first bond that's formed is going to be a sigma bond, and these additional bonds that are formed, multiple bonds, beyond one, are going to be additional pi bonds. Okay, so sp hybridization accounts for describing triple bonds, multiple bonds in general, double bonds as well, and allows us to describe these linear geometries. The next hybridization scheme we're going to look at is a so-called sp2 hybridization, and it turns out that this hybridization model allows us to describe trigonal planar geometries. Right? So the idea is going to be roughly the same. We're going to construct an orbital. We're going to call it an sp2 orbital. And as the name implies, it's going to be formed by adding in one s and two different p orbitals. So I'm writing out kind of a simplified version of the mathematics underpinning this process of adding together orbitals, where I'm basically saying, okay, I'm going to have some function representing the s, in two of the different p orbitals. I'm simply mathematically combining these guys. Now, if I combine three different atomic orbitals, what you're going to end up with are three different hybrid orbitals, all with the same energy, and that energy, of course, as we saw last time, is going to be some intermediate value between the energy of the unhybridized s and p. And that's what this energy diagram is illustrating for us. And so in this case, in the case of sp2 hybrid orbitals, we are going to be leaving behind a single unhybridized p orbital. Okay, so from an energetic standpoint, we have these three equivalent sp2 orbitals. And from a geometric standpoint, we end up getting, as you might predict, an arrangement of these three oblong dumbbell-shaped orbitals, sp2 orbitals, where each one of those orbitals has one of their larger lobes pointing towards the vertex of a triangle. And so you end up at the end of the day with an orbital configuration like I have circled here, and this, of course, is what allows us to describe those trigonal planar geometries. And I want you to notice that because we're adding together an S, a PX, and a PY, this triangle is lying in that XY plane. You could, of course, carry this out combining PX and PZ. In that case, the triangle would be in the XZ plane, right? Energetically equivalent. It's really arbitrary how do you want to define your axis system. Okay, but at the end of the day, what I want you to keep in mind, right, is that, if, like, for example, if we take carbon, right, we form sp2 orbitals, we are coming up with three energetically equivalent orbitals. And when you have three energetically equivalent orbitals, you use Hund's rule when you are distributing out those electrons. Now, another interesting result occurs here that I've illustrated. Notice that for carbon, right, which we know has a total of 4 valence electrons, when we write out that hybridization scheme, even though you know that the sp2 orbitals are lower energy than the p orbitals, we actually end up with a scenario where one electron goes into each of the sp2 orbitals and one electron goes into that higher energy p orbital. This can be a point of confusion. At first glance, it seems like I'm violating that Aufbau principle of putting electrons in their lowest energy orbitals first. Well, to answer that, you have to remember that this hybridization process isn't something that occurs on an isolated atom. If it was simply an isolated atom, there wouldn't be hybridization. Everybody would just be hanging out in their standard s and p orbitals. Hybridization occurs when other atoms are in close proximity. So when those other atoms are in close proximity, you then change the energetics, and the energetics change in such a way that this sort of electron configuration is really the best description for that carbon atom. And the result then is 3 hybrid orbitals that all have this trigonal planar geometry with this 120-degree bond angle between them. And then I'll go ahead and try and draw this in blue. Going above the page, sticking out at you and going back into the page, is another unhybridized p orbital, kind of sticking out and going back in right there. Okay, and so this has some important implications, right? But it's important for us to remember that this is not a violation of the Aufbau principle, because it's something that's occurring when we are forming molecules. Okay, so to appreciate this, let's go ahead and look at an example, a simple example, formaldehyde here, where we have a little bit more complex Lewis structure, carbon, oxygen, and then 2 hydrogens here. We've drawn out the electron configuration for these guys. We know that this carbon atom, right, from our Lewis dot model, has a trigonal planar geometry. Therefore, we are going to choose an sp2 hybridization scheme, and we are going to make these carbon sp2 orbitals shown in purple in this figure. Each one of those sp2 orbitals is then going to have a single electron. Remember, for the carbon, you've got sp2, we're going to have a single electron in each, and then another electron in that unhybridized p. So those are these electrons that I'm circling right here, right? So one each of these guys are in this carbon geometry or carbon electron configuration. Okay, then once you have those orbitals laid out, you can form sigma bonds with the hydrogen by overlapping with the hydrogen 1s, another one right here, and then you can overlap with oxygen 2p orbitals. One of them head-on overlap to get a sigma bond, and then a side-to-side overlap, which of course happens on the top and bottom of the plane of that molecule, to get a pi bond, your multiple bond, right? And thereby we've effectively built up a valence bond model for formaldehyde, accounting for this multiple bond. Okay, now you might be able to predict the next one. The first example, we used an S and 1p, then we did an S and 2p's to get trigonal planar geometries. Well, the next step is going to be to predict and describe the bonding in tetrahedral molecules using an sp3 hybridization scheme. All right, so once again, from a mathematical standpoint, we're adding together S and 3 different p orbitals. So we're adding them all together. And so however many atomic orbitals you add together, that's how many hybrid orbitals you form. All those hybrid orbitals have the same shape, the same energy, and just possibly different orientations. And so the different orientations now, in the case of sp3 hybrid orbitals, once again, as you would probably expect, are pointing towards the vertex of a tetrahedron. Each one of those larger lobes on the sp3 orbitals are pointing towards the vertex of a tetrahedron. In other words, you put them all together and you have a tetrahedral arrangement of hybrid orbitals. Now you couple this with the fact that you now have 4 equivalent sp hybrid orbitals and 1 electron in each. Well, you now have a situation where each one of those orbitals, for example, could overlap with each one of those half-filled orbitals could overlap with the half-filled orbital for hydrogen, and we are able to predict CH4 correctly, and which was one of the core challenges that we, of course, used to motivate this idea of hybrid orbitals. So to make a little bit prettier picture of what I just tried to draw here, right, we can look at the example, right, of methane a little bit more closely. where we've got our sp3 orbitals, hybrid orbitals in purple, and then the 1s orbitals on hydrogen. And again, mathematically, you can do the math here, and you'll find that carrying out the proper combination of these atomic orbitals gives us the hybrid orbitals with the desired 109.5 degree bond angles. And this structure here maximizes orbital overlap for bonding. Now, just because I've hybridized the orbital doesn't mean that hybrid orbital has to be involved in a bonding interaction. The example here over here on the right-hand side shows ammonia, where we once again need sp3 hybrid orbitals in order to account for the trigonal geometry. But the orbital up top, the sp3 orbital up top, just has a lone pair of electrons. Okay, so this really is a very flexible theory, right? We're making hybrid orbitals, accounting for geometries. These hybrid orbitals will hold, any types of electron pairs, single electrons, or bonding electrons, you name it. Okay, but of course the same rules apply to any quantum mechanical orbital. You can't have any more than 2 electrons, and when you have 2 electrons, they need to be spin paired, one up, one down. All right, so we're still holding to those basic tenets of quantum mechanics. All right, so the next step then, we've gone SP, SP2, SP3. We now need to consider situations where you might need more than 4 sets of electrons being accounted for around that central molecule. So we saw that this is something that happens when you have expanded octets, when you're in that third row or below. And so in order to account for these more complicated bonding arrangements, what we're going to have to start doing is pulling in d orbitals. And remember when back in the previous section when I told you to watch out for these expanded octets, and I told you the situations under which expanded octets will actually form, I said, well, it only happens third row and below because you need to have d electrons that are close in energy. In order for these orbitals to effectively overlap and for us to make these hybrid orbitals, they need to be close in energy, right? So close in energy, d orbitals allows us to add in one additional bonding arrangement here to get us our trigonal bipyramidal structure, or 2 d orbitals pulled in here to get an octahedral arrangement in these hybrid orbitals. But notice again, these hybrid orbitals, whether they're sp, sp2, sp3, sp2d, sp3d, sp3d squared, all of these guys have this same sort of asymmetric dumbbell appearance, where the small end is kind of covered up by the other orbital, on the other side of the molecule. Okay, so very similar. The real difference here that's coming in is simply the orientation and number of these asymmetric dumbbells that are forming. Okay, so the process then for determining the hybridization scheme in the molecule is really quite straightforward, right? We're really not doing much more than what you already know, right? Your first step to describe the hybridization in any molecule is to draw that Lewis dot structure. In this case, we're dealing with an AsF5, right? Arsenic pentafluoride. In this case, we've got 5 fluorine atoms surrounding that central As element, and as a result we're going to have in the Lewis structure a total of 5 electron groups, and so 5 electron groups corresponds to our trigonal bipyramidal structure. All right, and so we know in order to get that trigonal bipyramidal structure, then we're going to need to hybridize the s, all 3 of the p's, and a single d orbital. Right, and then those hybrid orbitals will be able to overlap with p orbitals in the fluorine, and bingo, you're able to account for bonding in this trigonal bipyramidal structure. Okay, similarly, if we have an octahedral structure like sulfur hexafluoride, right? Once again, we draw that Lewis dot structure. We see that we have an octahedral geometry, so we say, well, in order to account for an octahedral geometry, I now need an s, all 3 p's, and now 2 d orbitals, right? And our bonding interactions are described as illustrated here on the screen. Okay, so you now have everything you need to determine hybridization, right? And it really is a very simple method. Two-step process. You're going to use VSEPR. You're going to use everything you did before, VSEPR and all the background there, make that Lewis dot structure, identify the optimal geometry, right, to determine the electron geometry, right? And we care about electron geometry because remember, we need to look at lone pairs and bonding electrons. They all need orbital homes. Right? Once you find out how many electron groups there are, what that electron geometry is, you simply assign the hybridization scheme based on that geometry. If you have 2 electron groups, you're going to make a linear molecule, you need sp hybridization. If you have 3 electron groups, you're going to have a trigonal planar VSEPR geometry, or electron geometry from VSEPR, and an sp2 hybridization scheme. And of course, it just continues in this way. 4 electron groups, you're going to have a tetrahedral electron geometry. You're going to need an sp3 hybridization. 5, trigonal bipyramidal, sp3d. 6, octahedral, sp3d2. All right then. So to close things out, we've done an awful lot here in valence bond theory, but now you really do have everything you need to start solving general problems, right? So the key things to remember. Hybrid orbitals, everything we talked about here in terms of hybrid orbitals, they do not exist on isolated atoms. They're only formed to help account for and provide a simplified description of bonding in covalently bound atoms, covalently bound molecules where these atoms are tied together. The shape of these hybrid orbitals depends both on the type and number of atomic orbitals used in their construction. So we saw that, sp, sp2, sp3, they change. Their orientation and the number of these orbitals change, right? Depending on both of those factors playing in, right? So the third thing we need to keep in mind here is that whenever we're forming a set of hybrid orbitals, right, we're making this set of hybrid orbitals by combining a set of atomic orbitals. And you're always going to have the same number in each set. If you have 2 atomic orbitals you're combining, you're going to get 2 hybrid orbitals out. If you have 3 atomic orbitals you're combining together, you're going to get 3 hybrid orbitals out at the end of the day, right? And all of the orbitals in a given set of hybrid orbitals are equivalent in both shape and energy. The only difference is that they're oriented in different directions, right? And the type of hybrid orbitals formed in a bonded atom depends on its electron bearer geometry based on VSEPR. So all you have to do is find that VSEPR geometry, figure out the number of electron groups, and map it on, as we saw in the last 2 slides, sp, sp2, so on and so forth. Okay? And then remember, we always have to keep in mind these different types of bonds. Hybrid orbitals overlap to form sigma bonds, and then what we're typically going to be seeing is unhybridized orbitals, p orbitals, overlapping to form pi bonds, right? So for our purposes, number 6 is always going to hold here, and that's going to allow us to, really predict and understand the bonding and really all of the simple compounds that we've been building Lewis dot structures for. And so in the next video, we're going to look at a handful of examples of doing just that, building up predicting the hybridization scheme for a variety of different molecules.